Hi, my name is Kaylee Valone. In this video, I will discuss the improbability of Ant-Man by determining his density at certain sizes and comparing that to other earthly densities. I will also discuss the square-cube law in relation to Ant-Man. So, Ant-Man and the famous Pym Particle. This particle reduces the space between atoms while increasing density and strength. We will be ignoring this fantasy particle for the sake of this video, and instead focus on the real-world implications of shrinking someone using Galileo's square-cube law. The Pym particle theoretically allows its user to bypass the square-cube law. The square-cube law states that if you make a cube that is solid twice as high, you get a cube that is twice as big in each dimension. This makes the volume 2 by 2 by 2, or 8 times the original volume, and therefore 8 times the mass, which is proportional to the volume. However, the muscles and bones in a man would, if enlarged to twice the height, be only 2 times 2, or 4 times the area, and therefore only 4 times stronger. So by doubling the size in each dimension, we have only quadrupled the strength of bone and muscle, whereas the weight has increased by a factor of 8. If held to this law, Ant-Man's bones would collapse under this weight. I am able to use this law to find the volume of any object, and will apply it towards eventually finding the density of Ant-Man at specific sizes. To find the volume of a normal Ant-Man, we find length times width times height. For this scenario, his height is 2 meters, shoulder length is going to be 20 centimeters, and torso width is going to be 20 centimeters as well, and those convert to 0.2 meters. So we plug those in for the volume equation, 2m times 0.2m times 0.2m. That's going to be 0.08 kilograms per meter squared cubed. We know his mass to be 80 kilograms, so we now know Ant-Man's normal volume and his mass. We plug those into the equation for density, which is mass divided by volume. So 80 divided by 0.08, which is going to give us 1,000 kilograms per meter square cubed. This is the density of water and of normal humans. Finally, we find the scale of Ant-Man down to his namesake, the ant. I chose the average bullet ant at a height of 2 centimeters, because we are reducing Ant-Man's size from 2 meters down to 2 centimeters. We divide his original volume by the reduction factor of 100 cubed instead of multiplying. So his new volume will be 0.08 divided by 100 cubed, which is also 1 million. That will be 0.0000008 meters cubed, or 80 millimeters cubed. So now that we know his mass and then his new volume, we can find density. So 80 divided by 0.0000008, that will equal 1 trillion kilograms per meter squared. So this density is as dense as the average white dwarf star. So Ant-Man should realistically be tearing the Earth apart. It should just all kind of collapse in on itself. Another issue that would be caused of being this small would be heat retention and energy consumption. If anybody was to be this small, then they would have to be eating an insane amount of food to be able to produce the amount of heat needed to escape hypothermia. So there you have it. According to the square-cube law, shrinking and expanding anyone to the scales that Ant-Man achieves is simply not possible without some fancy mystery particle. The mathematical process allows us to explain why certain biological processes would not work at that size in relation to the object's volume and strength. Thanks for watching!